this lesson is, what does the graph of the derivative tell us? This is an interesting lesson in fact that you are not going to need your pencil or paper or calculator to do this work. All you need to do is two things: watch and listen. Now, it will be helpful if you know certain things. That is, you know what a critical number is on a graph. And you know how to find critical numbers. That is, where the first derivative equals 0, among other things. You need to know whether the critical number is a relative maximum or relative minimum. So you need to know the relationship between derivative and an increasing and decreasing function. It'll also be helpful if you know what is a point of inflection. And if you know that they occur when the second derivative is 0, and that the second derivative is negative. When it's negative, means concave downward, and when the second derivative is positive, is concave upward. But we're just throwing some terms at you now. Don't try to figure those out. We're just telling you information that will be helpful for you to know, so that all you have to do is listen and watch. So try not to panic on this. Once you get the hang of this, this should be quite simple, or quite simple a task for you to undertake. So let's look at a graph. Now, this is the graph of the derivative of a function, not the graph of a function, but the graph of its derivative. Let me give you, for instance, if I gave you the function y equals x squared, that's a parabola. We know that we could graph that. The derivative of y equals x squared, y prime, is 2x. That's a straight line. If I gave you the graph of 2x and asked you to describe the original function, that is what we're talking about. That is what we're undertaking here. We're giving you the graph of the derivative and asking you to think backwards. Okay. Give us the original function, the description of the original function. Now, you're going to have to get used to this. The x-axis is the x-axis, but normally when you graph a function, this is f of x, the y-axis. But this is no longer, this particular graph, this is not the y-axis, but the y prime axis, the derivative. Now, everything above the x-axis when you're graphing, no matter what, is positive territory, and everything down here is below the x-axis is negative territory. So since this is the graph of the derivative, that means the derivative is positive when the graph is up, of the original function is positive when it's up here, and if the points are down here, it's negative. Okay, so you see on this graph, this is the graph of the derivative, points labeled A, B, C, and D. Now look at A. A is on the x-axis. In other words, it's 0 here. The output value is 0 here. What's the output value? Derivative. The derivative is 0 here. That means this is a critical number. Now, to the left of A, the graph is above the axis, the x-axis, which means positive. So that means derivative is positive to the left of A. And derivative, it tells us the graph is increasing to the left of A. To the right of A, the graph is below the x-axis. That's negative territory. That means the derivative is negative, or it's decreasing. So we know this is a critical number, and to the left, the graph is increasing, and to the right, the graph is decreasing. So A is a relative maximum. Let's come over here to C. Again, the first derivative here is 0, so this is also a critical number. And to the left of C, it's negative. It's down here. And to the right of C, it's above the axis. It's positive. So this means it goes from decreasing to increasing. So that means that C is a relative minimum. Relative maximum, relative minimum. So that's what they are. In addition, since the first derivative, it's increasing until you get here, this function is increasing from its beginning, way of minus infinity to a. And then it's down here, it's decreasing, it's negative till you get to C. So from A to C, it's decreasing. And from C, the rest of the journey out to infinity, it is increasing. So we have a lot of information already. We know this is a turnaround point and it's a high point. We know this is a turnaround point on the graph. It's a low point. Now, we want to say one more thing about this graph. See this point B? The slope of the line tangent here is 0. Now remember this, in other words, the slope. But this is the graph of the slope. So this is the slope of the slope, which is second derivative. So the second derivative is 0 here. The slope of the first derivative's graph, which is second derivative, is 0 here. That means that B is a point of inflection. Now let's look at the slope of this line to the left of B. In other words, the tangent to the graph. It's downhill. In other words, the second derivative. Remember, you're looking at the graph of the derivative. So when we want the slope of the derivative graph, we're talking about the second derivative. So the second derivative is negative till you get here. So that means the graph is concave downward till you get here. And now the slope is positive. Slope of the line tangent to the graph is positive till you get all the way up here. So that means it's concave upward after you pass B. And then the second derivative here is also negative. So this is another point of inflection. And so to the right of it, it has a positive slope. So it's concave upward. Okay. So we have concave upward, concave downward, concave upward. So we get a lot of information from the graph of the first derivative. Hold on to that because we're going to talk about that even more before we leave this. We're not going to desert you. We've made every attempt for you to understand what's going on so that you could look at a graph of the derivative and answer bang, 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 everything you need to know. It really, once you see it, it becomes very simple. We're going to look at the graph of the second derivative. We are not really interested in the graph of the second derivative, but we're going to look at it right now because it's interesting. This is the graph of the second derivative. The graph of the second derivative gives us nowhere near the information that the graph of the first derivative does. That's why we're not going to dwell a lot on the graph of the second derivative. But it is interesting. This is the graph of the second derivative, which means the y-axis is f double prime of x, or when the graph is above the x-axis, that means the second derivative is positive, and when it's below, it's negative. Now remember, second derivative above positive area means concave up. Second derivative in negative means concave down. This is where the second derivative is 0. Okay, right here, the second derivative is 0 here. Okay, so that means it's a point of inflection. And since it's below there, the second derivative is negative down here, so it's concave downward. Then it's above the x-axis, concave upward. And this is another point of inflection, and then it's followed by it's in the negative territory, so it's concave downward. Again, worry more about the first graph of the first derivative than the second derivative. All the second derivative graph does is supports what we found from the first derivative. We really gleaned no new information here. The only thing I guess I could tell you is if somebody gave you the graph of the second derivative and asked you to describe the first derivative, you cannot describe it as well as you can given the graph of the first derivative. So we're doing the second derivative simply because we can, basically, at this point. Now, what you see here called figure 3, this is the original function. In other words, what we did is we took a function and then we graphed its derivative, and we showed you that in figure 1, and then we graphed its second derivative, and we showed you that in figure 2. Let's see. This is the original function. Now, the original function has a relative max here. That's easy. And a relative min here. And this looks like a place where it changes concavity. So this is probably the PI. And it's increasing until you get here. And then it's decreasing till you get here. And then it's increasing till you get here. Okay. And then we have it's concave downward till you get here. And when you're given the original function, it's very easy to answer the questions. But the question I want to say, let's go back to the first graph. What did we find out here? We found that this was a critical number, and to the left of it, it was positive, and to the right, negative. So this was a relative max. Let's go to the original graph. It indeed is a relative max. If we go back to that first figure, this is the other critical number, and that turned out because it's negative followed by positive, this is a relative min. Let's fast forward here. It is a relative min, okay? And then we found back here, we found that B and D were points of inflection, and they are indeed places where the changes concavity, concave downward, concave upward. It's hard to see, but if we did, because we didn't really show much of the graph after that, but it's going back to concave downward again. So this is a very good visual. What you should do is take a problem like our number 1 and see if you can answer the questions, then look at the original function. You can make up problems like this for yourself if you have a graphing calculator. Have a function, graph it, trace its graph, sketch its graph. Then take its derivative and look at the graph of it using your graphing calculator and see if you can take the graph, the sketch you have of the first derivative, and see if you can describe what the original function looked like. In other words, you can create this type of problem yourself and practice and make up problem after problem after problem until you get pretty good at it. Okay. Here we have what we've done here is we've graphed a function. The blue function is the function. We've graphed its derivative, that's the red graph, and we've graphed its second derivative. And this is just another way of showing it all on one graph. You have to be able to kind of block out. In other words, let's look at the red graph. Can you tell me where the critical numbers are? Well, it's where the first derivative is 0. Here's 1. We'll look at the original graph. There it is, right above you. Check yourself out. Where's another critical number where the first derivative is 0? Right here. And look, it sure is. There it is. And what is it? Well, to the left, it's above the x-axis. That means increasing versus decreasing. So this thing must be a relative max, and it is. And then we look at here, and the to the left, the graph is negative. followed by the slope is negative, or decreasing followed by increasing. So this must be a relative min, and it is. So you can check yourself out right there. And then we see that this first derivative has the slope of the tangent line to the first derivative right here is 0. That means the second derivative is 0 here, and that means this thing must be a point of inflection where it changes concavity, and it does. So this is an interesting way you can see all for yourself. And then, of course, this is a graph of the second derivative, which we've just thrown it in because it's there. The only thing you get from it is that the second derivative is 0 here, so it must be a pi, and it must be, since it's in the negative region, it must be concave downward, and it is. And here it's second derivative is a positive, so it must be concave upward, and it is. This is a great all-in-one. The only thing about it is you have kind of a try to want to peak too early. So if you have an ability to look at the red graph and ignore the rest, answer it, then take a peek at the original function, that would be nice. And then we come down here to figure 5. This is just another one of them, 3 for the price of 1. It's a little more complicated, which, in other words, we have more critical numbers. The red graph is the original function, the green graph is the graph of the derivative, and the purplish graph is the graph of the second derivative. And the main thing is, like you said, answering questions from the red graph is no problem. Finding critical numbers, bang, 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 that's easy. Determine whether it's a min or max. It's a min here, it's a max here. Not interesting at all. Like I said, you could probably show somebody the red graph and ask them, and having no knowledge of anything in calculus about slope and derivatives, they'd be able to answer the question. What your chore is to do is to focus on the green graph. The green graph says it crosses the green graph, which is the first derivative, it crosses the x-axis here. So we must have a critical number here, and we do. And it crosses it here, so we must have a critical number here, and we do. And the green graph crosses here, it must be a critical number, and it is, okay? And not only is it a critical number, we know that to the left it's negative, to the right it's positive, which means it's a relative min, and it is, okay? And so forth and so on. We don't want to make more out of this than is, but these are great sources of problems for you to work on. We finish up with another. We want to ignore now the second derivative graph because we've had it there, but we really want to make sure you understand what is going on with the graph of the first derivative. So here you have it. Let's see if you can go at it quickly. This is the graph of the first derivative. So that means the first derivative is 0 here, 0 here, and 0 here. So A, C, and E are critical numbers, okay? Now, to the left of C, the graph is up above. To the right of C, it's below. So this thing is increasing till you get here, and it's decreasing after you pass here. So this is a relative max, okay? And likewise here, it's decreasing followed by increasing. So this is a relative min. Now, this is a critical number, but it's one that's not a relative max of min. It's a pi, okay? It's a pi. Likewise, B is a pi, and D, it's where the second derivative is 0. The second derivative is 0 here, here, and here. So how do you find critical numbers? It's where the first derivative is 0. Well, it's here, and it's here. So they are critical numbers, okay? This one turns out to be a relative max. This turns out to be a relative min, because on each side of C, it's in the negative region. This turns out not to be max or min, but it's a PI. Okay, but then we have down here two additional points of inflection. They're not critical numbers, but they're where the second derivative is zero. In other words, the slope of the first derivative is zero. So if you can just kind of look at something to say, where it crosses the x-axis are critical numbers. So critical number, critical number, critical number. Okay. Above and below, relative max. Below and above, relative min. The same on each side. It's neither max or min, so it's a PI. Okay, before we leave, the slope of the second derivative here, horizontal, that's a PI. This is a PI, and you're more or less done with the question. Don't want to oversimplify it, but if you once catch the hang of it, you can look at a problem and basically answer it in short order. Okay, so this is a very interesting lecture. Giving you graphs of the derivative of something that have become in vogue in recent years of calculus, mainly because we have the graphing calculator. And so it's very easy for students to take the function given and not know any calculus and simply graph it. This type problem requires that you have an understanding of calculus. In other words, the graph, when you're given the graph of the first derivative, you don't have the function. And so graphing utility is really of no advantage for you here. And so what we have here is we are concluding this lesson, and we hope if you need to that you'll replay this time and again until you really take ownership of it, because once you do, it's should be a fairly easy topic. So we're leaving this lesson at this point.